Welcome to a deep dive into the fascinating world of training neural networks. Today, we're demystifying two fundamental algorithms: gradient descent and backpropagation, the bedrock of nearly all deep learning advancements. Without them, our complex AI models simply wouldn't learn. Imagine you've built a powerful deep neural network, but right now, it's just a collection of random connections. To make it intelligent, we need to teach it, allowing it to adjust its internal parameters, or weights, until it can accurately perform a task, whether that's recognizing images or translating languages. This learning process is an optimization problem. We want to find the perfect set of weights that minimizes our network's errors. This is where gradient descent steps in. Think of it as navigating a foggy mountain range, trying to find the lowest point, or the valley, purely by feeling the slope beneath your feet. To know which way is down, we first need a way to measure how wrong our network is. This is achieved using a loss function. The loss function quantifies the difference between our network's predictions and the actual correct answers. A high loss means our network is performing poorly. A low loss means it's doing well. The gradient is the crucial piece of information that tells us the direction and magnitude of the steepest descent of our loss function. In simpler terms, if our loss is the mountain, the gradient points towards the steepest uphill path. To minimize loss, gradient descent tells us to move in the exact opposite direction. Gradient descent works iteratively. It starts with an initial set of random weights. Then, it calculates the loss for the current state. Based on this loss, it computes the gradient. Finally, it takes a small step in the direction opposite to the gradient, updating the weights, aiming to reduce the loss. This small step is governed by a hyperparameter called the learning rate. A learning rate that's too large might cause us to overshoot the minimum, bouncing around erratically. One that's too small will make the learning process excruciatingly slow. Finding the right learning rate is critical for efficient training. While gradient descent provides the strategy for weight updates, a critical question remains: how do we these gradients for every single weight in a vast, multi-layered deep network? Manually computing these derivatives for millions, or even billions, of parameters is practically impossible. This is where backpropagation enters the scene. Backpropagation is an ingenious algorithm that efficiently computes the gradient of the loss function with respect to every single weight in the network. It does this by essentially propagating the error backward from the output layer through all hidden layers to the input. The mathematical backbone of backpropagation is the chain rule from calculus. It allows us to calculate how much each weight contributed to the final error by breaking down the complex derivative into a series of simpler, localized derivatives, layer by layer, starting from the output and moving backward. In practice, backpropagation first performs a forward pass where input data flows through the network, generating a prediction and calculating the loss. Then, during the backward pass, it computes the gradients for each weight, using the chain rule, telling us how each weight should be adjusted to reduce the loss. So, gradient descent is the optimization algorithm that uses the calculated gradients to update weights, and backpropagation is the incredibly efficient method for calculating those very gradients in deep networks. Together, these two algorithms are the fundamental engine driving the learning capability of nearly all modern AI.